So something we talked about in last class, was mechanical energy, which is the sum of potential energy and kinetic energy in a system. Okay, we've been using these terms a lot lately, and I just wanted to take some time for us to actually really understand what potential energy and what kinetic energy is in a system. Okay, a system. So here we have a system which is a roller coaster. And let's assume that that roller coaster is isolated. It means that all the energy that is inside of this roller coaster cannot leave, and no more energy from the outside can come in. If a system is isolated, it is removed from the environment. And in that way, we can track the energy going from one form to another, and that energy will be constant. So this cart right here that's moving, it has motion energy, which is called kinetic. The energy of movement is called kinetic energy, Ke, all right? And that energy, it can be used to do many different things, okay? If that nothing is working against that cart moving, that kinetic energy will be constant. If there is friction, that cart is going to end up slowing down because friction is going to do work against that cart, and the kinetic energy will be used up and eventually go down to zero, and the cart will stop, okay? In this system, let's just imagine that there is no friction, all right? Then the work that's happening is that that cart is going uphill. If it's going uphill, it's working against the force of gravity, right? So the cart has the force of gravity, and it climbs up a distance, d, and we know that work is equal to force times distance. So that kinetic energy, which is the energy that it has, is going to be consumed by doing work against gravity. All right, so in that case, I can say the work against gravity is going to be mgh, where h is the height. Okay, so let's call that h. G is the acceleration of gravity, and m is the mass. Mass times gravity is the force of gravity. All right, so the energy that we have to put in to make this cart climb up is equal to mgh. All right, now where does that energy go when the cart gets up here? Well, that energy is stored. We did work. It didn't disappear because the system is isolated. And so now that cart at the top of this hill has what we call potential energy. It has energy that can be used, that can potentially be used to do work. And in this case, when it's up here and if it continues moving downhill, that potential energy will be used to be converted into kinetic energy. Gravity will perform work on this object downwards and release that potential energy. So all that potential energy will then become kinetic energy. And what we see in this position is the cart is somewhere in between the top and the bottom. So as this cart rolls down, it's going to be losing potential energy and gaining kinetic. So according to this graph, which makes sense, this cart is a little more than halfway down. So if it's a little more than halfway down, more than half of the potential energy has been converted into kinetic energy. So it has a little larger amount of kinetic energy than potential energy at this point. And if the cart ends up on the bottom, then all of that potential energy will be converted to kinetic energy, and we get our graph where the kinetic energy is here, and there will be no potential energy now that it's back at the bottom, okay? And this is the sum of the kinetic energy, potential energy in a system is called mechanical energy. So I just wanted to give you that little brief note as you watch this video so we understand when we talk about mechanical energy and a question asks about how much mechanical energy is in a system, you'd have to find the potential energy in a system and the kinetic energy in the system. So let's try to practice that. Let's take a look and give you a situation. So I'm going to draw a situation for you. Another roller coaster situation. Okay, and here we have, Okay, so here we have a roller coaster that looks like that. Okay, and we have different positions of the roller coaster. We have position 1, which is 100 meters. You have position 2, which I'm going to write this down. Position 1, position 2, and we have, let's make that a little bit better. We have position 3. Okay, now position 1 is 100 meters. Position 2 is 20 meters, and position 3 is right down at the bottom at 0 meters. Okay, and let's say the cart is 100 kilograms. So if I want to calculate the total mechanical energy, so let's calculate total mechanical energy. At all 3 points. Okay, well, what we need to do is we need to calculate the potential energy, and we need to calculate the kinetic energy. So the potential energy stored inside of that cart at the top point is going to be the work that we did to bring it up there, the work that we did against gravity. Okay, so the potential energy is equal to mgh, the force times the height. That's the work that we did to get it up there. All right, and how do I calculate the kinetic energy? Well, kinetic energy has a formula that looks like this, 1/2 mv squared. So if I know the velocity of a cart, and I know the mass of the cart, and I can plug it in here and calculate the total kinetic energy. Now let's say at this point that the cart has a velocity of 0 meters per second. It's not moving, all right? And all of a sudden the wind blows and it just pushes it to the edge and it starts to roll down. Okay, so it didn't really have a velocity, but at this point over here at 20 meters, it probably will have a velocity, and at that point it will definitely have a different velocity. So the kinetic energy is going to grow. Okay, so at position 1, how do I calculate the total mechanical energy? Well, the total mechanical energy is only going to be really potential energy, but remember, total mechanical energy is equal to the PE plus KE, okay, potential energy plus the kinetic energy. So my mechanical energy is going to be equal to mgh plus 1/2 mv squared at any point in time, okay? So at the top point, my velocity is 0. So let's plug these numbers in to calculate the total mechanical energy. So at position 1, okay, I have a mass of 100 kilograms times 9.81 meters per second squared times 100 meters. I think that's what you said, yep. Plus 1/2 times 100 kilograms times 0 meters per second squared. Okay, well that just cancels this out because 0 times all that makes it 0. So I have 0 kinetic energy here. And now if I multiply this through, I am going to have joules of energy. Okay, so the total mechanical energy is going to be 98,100 joules. Okay, and according to the laws of conservation of energy, all right, I think 98,100 joules should be the total mechanical energy in that entire system, because let's imagine the system is isolated. Energy can't come in and energy can't go out. Well, in that case, it should be constant. 98,100 joules should be the total mechanical energy throughout this entire system. Okay, so we figured out at position 1 we have 98,100 joules. Okay, now position 2, according to what we just said, the total mechanical energy should be the same. It should be 98,100. So mechanical energy is going to be equal to the potential energy at that point plus the kinetic energy at that point. So again, mgh plus 1/2 mv squared. And if you add them up, they should be equal to 98,100 joules if energy is constant and it's isolated. So using this setup, I could potentially calculate the velocity of that cart right at this point at position 2. All right, let's take a look. So 98,100 joules is equal to 100 kilograms times 9.81 times 20 meters. Okay, so that's the potential energy at 20 meters, plus 1/2 times 100 kilograms times V squared. Okay, with this setup, I'd be able to isolate V and be able to calculate. So 98,100 joules divided by, or subtract 100 times 9.81 times 20 meters divided by 1/2 times 100 kilograms. And if I square root all of that, that would give me my velocity. So we have a way of calculating the velocity of an object at that point. All right, so using that, our knowledge of total energy. So at this point, the total mechanical energy, if I had my potential energy and kinetic energy, the total potential energy is equal to my mechanical energy at that point. And at this point over here, if I drew my graph, I'll have a little bit more kinetic energy, like probably 80%, and a smaller amount of potential energy. And at this point over here, I will have no potential energy and all kinetic energy. Okay, so I can visualize this exchange. And the values of these bars put together would always equal to 98,100 joules. Okay, so at position 3, again, the mechanical energy is going to be equal to 98,100 joules, like we calculated before. And it's going to be only equal to my kinetic energy because I don't have any potential energy at that point. I'm back down on the ground, okay? So all that gravitational potential energy is converted into kinetic energy. So in this case, I could solve for the velocity at that point by looking at the formula for kinetic energy. So then 98,100 joules divided by 1/2 times 100 kilograms square rooted will give me my velocity at the bottom. Now I didn't solve these on purpose, okay, so that you can take a look and try to figure out, does the velocity grow as the roller coaster reaches the bottom? But the important thing in this little video is to understand that mechanical energy of a system is the sum of its potential and its kinetic energy. And that mechanical energy is conserved as long as the system is isolated. None of the energy can go in or out. Okay, and that there'd be no friction, because then energy would go into friction like we talked about in class. All right, so hopefully this video helped you understand how we can use the concept of mechanical energy to calculate the velocity of an object that's going up and down a ramp or up a hill, okay, by understanding it in terms of what is the mechanical energy of the system.